So this talk is about designing an automatic gain control for the original bladeRF. The original bladeRF's RFIC did not exactly have an AGC, so I'm going to go into the design and the design decisions behind implementing said AGC. Just as a little bit of an introduction about myself, I'm the founder and owner of Nuon LLC. I have interests in software, hardware, RF engineering, as is pretty much required by anyone doing anything in SDR. Previously, I was building enterprise network equipment at Cisco. Was there for about a couple of years, a bunch of years. I worked on the first generation AC access points that existed, and I'm a longtime information security researcher, mostly been independent in that career. So Nuon is known for the bladeRF, which is a low-cost USB 3 software-defined radio. The product line is used by thousands of engineers, hobbyists, and researchers. Many of you here are familiar with it, if not actually already customers. We launched the first crowdfunding campaign for the original bladeRF in 2013, and we recently revamped the product line with the bladeRF 2 Micro. We have a couple decades of combined engineering experience in software-defined radio, enterprise network equipment, and defense type work. Our focus is on low-cost software-defined radios and applications. We support GNU Radio, GRCon18, SDR, BTS, SDR, Sharp. We kind of pride ourselves on our lightweight C library and API and command line interface. And we have general support for Linux, Windows, OS X, and all sorts of BSDs. The original bladeRF was, as I said, basically a Line Micro 6 based device with a USB 3 transceiver from Cypress, and it featured an Altera 4 FPGA that basically glued all the logic stuff together. It also had a pretty nifty SI5338 synthesizer, which is Silicon Labs' kind of like top-of-the-line synthesizer. Here's sort of like a rough block diagram of the bladeRF, which, again, basically USB 3 transceiver hooked up to the FPGA, hooked up to the RF front end with a clock distribution chip that basically feeds everything its fundamental clocks. The underlying block diagram for the front end chip is pretty much what we kind of know to be a standard 0IF architecture for a transceiver. So digital pins are on the left, and your RF pins are on the right, and all the baseband and mixing and LO stuff is just generated within the chip. So digital signals come in on the left if you're transmitting. They go through a D to A. Things are baseband filtered. There's a baseband amplifier, which then feeds things into a IQ modulator, which has a LO source that is on the chip, and things get bumped up to RF. And then the TX VGA2 amplifiers amplify the outgoing signal, and you basically end up going from digital bits to RF. The reverse happens on the receive side, where an inbound electromagnetic wave is amplified by current source LNA. Things are mixed down to baseband in the RX mixer. There's a couple gain stages and baseband filters, and eventually everything is digitized into digital IQ samples, and things are exposed via digital interface. As you can kind of see, there's not much in the way of a AGC on this chip. So realistically, some of the waveforms that we had developed, we're seeing things coming in as low as like minus 110 dBm to like about as hot as minus 25 dBm. So that's about 85 dB of range. The problem with this is there's just not enough range in those 12 bits to be able to see everything from minus 110 dBm to minus 25 dBm. So with each bit having roughly about 6 dB of static range associated with it, that's about 72 dB of static range. So it's not exactly possible to have a gain setting where you can have signals that are coming in at minus 25 dBm and minus 100 dBm be simultaneously visible to you. So, so how do we get a front end that can listen to a minus 110 dBm signal as well as a minus 25 dBm signal? The answer is obviously an AGC. So because things can't occur simultaneously, this means that gains have to be changed on the fly. So this kind of works well with digital packets, where you can kind of change packets on a per packet basis by adjusting the RF front-end gains. So with the LMS6, there were 3 gain stages, an LNA stage, an RxVGA1 stage, and an RxVGA2 stage. So the LNA stage is an RF stage, and RxVGA1 and 2 were baseband stages. So by adjusting those gains, we can increase the dynamic range of the RF front end. And when you add up all the gains between their mins and the max, you can achieve a total dynamic range of about 66 dB for the LMS6, coupled with the static range, that's about 138 dB of total gain range for, or visibility range for the LMS6. So we kind of designed a AGC that targeted the LMS6 specifically at one point, but then we were like, hey, we've developed a decent number of things that use this AGC, so why not create something where we can kind of have a sort of AGC interface where we can have separate device cores that contain all of the hardware-specific logic in a separate core within that larger automatic gain control. So in this case, the user waveform diagram is whatever you're designing, be it a Bluetooth transceiver, be it a 802.11 transceiver, LTE transceiver, just some custom waveform. So the idea is to create a sort of automatic gain control that has pluggable modules for different RF front ends, but contain all the logic, such as the decision to change gains, hysteresis, and sort of like the higher logic things inside of the device-independent automatic, or the device-independent part of the automatic gain control, and then keep the things related to actually issuing things like SPI commands or asserting GPIO pins within the device driver core. So this is just good software engineering brought to HDL. And the motivation behind this is, as I said, basically unifying the AGC so it helps port, so you can more easily port your waveforms between devices. This is useful if you're doing things in GNU Radio, if you're doing things in your own bespoke C implementation of your waveform. And the idea is to have reusable front-end device drivers. So basically, you can write a device driver core that you can use either for this AGC or use it for other purposes in your own development. So the idea was to kind of also unify the behavior of several AGCs, because there are RF transceivers that do have AGCs, but achieving certain functionality, such as holding a gain setting, might be a little bit more tricky and require a little bit more work than other transceivers do. So the idea is to have the larger automatic gain control assert or have digital interfaces such as request a hold, and then verify that it's holding, and that have an output from that same AGC core that says that the signal is valid. And then also the idea is to unify such core metrics as settling times. So what order should the gains be adjusted in? Because there are 3 gain stages previously. We all kind of know about Fry's formula. So basically, it's best to first turn up the gain closer to the source of the incoming signal. So in this case, it's the LNA. And the whole idea behind the gain strategy is to combat an increase in the noise figure. So amplifiers, as we know, amplify both the signal and the noise. So the idea is try to get the signal away from the noise and the noise floor as quickly as possible. So the recommended gain tables for the LMS6 were documented by the manufacturer. So basically, looking at this, there were 6 separate gain stages. But the problem is that with 6 gain stages, you kind of run into a problem with adjusting. There's a certain amount of penalty to adjust each one of these gain settings, and the fact that there's SPI settings that have to be sent over the SPI bus. So I kind of wanted a fast AGC. So we found a way to compress these down to just 3 gain stages. So basically, the top 2 got coalesced into 1, the middle 2 got coalesced into 1, and then the bottom 2 also got coalesced into 1 separate gain setting, which we have called high, mid, and low. And the idea is to not actually have to change all 3 register settings for all 3 of the gain stages between between the higher level gain settings. So in this case, only 2 variables change when you go between low and mid and high. So now that we know the gain settings, how do we make this automatic? So how do we make this run? So with most AGCs, you basically want to turn up the gains as high as you can. So the resting idle state of the AGC should be the absolute max high gain setting, which in this case is the high gain setting. And it's better to hear a signal and have it clip than it is to not hear it and have it completely just be missed. So that's the logic behind just cranking up the gains to absolute maximum and having that be your idle stage. The AGC, as it's running, is constantly running an IIR on the power value of the incoming signal. So the AGC will see a hot signal and decide to decrease the gain when the incoming signal's power is within 3 dB of hitting the top value, or the full scale value of the ADC, which is 2048. So the problem is that there's a bit of group delay in the architecture of most transceivers. So you need to wait a little bit after you adjust your gain settings in order to see the new gain settled. So AGCs aren't exactly perfect when it comes to instantaneously adjusting their gains. So there's a little bit of settling time. So in the design of the AGC core, we basically had to keep that into account and insert these wait states in the AGC to allow everything to come through. Another issue is some signals have a very high crest factor, such as OFDM. So in order to combat that, there's programmable IIR that we implemented. So knowing your waveform, you can adjust certain settings in the device-independent part of the AGC core, so then you can have your AGC core not change gains on a per symbol basis or per sub-symbol basis. Another solution is hysteresis, so meaning that as soon as the AGC locks onto something at the beginning of a packet, to not allow it to go back down to a higher gain setting as soon as there's sort of like a lull in the transmission. So a hysteresis should be based both off of time and power value. So if you have some sort of like short fading, it probably wouldn't be the best idea to completely undo the packet immediately. Maybe you should wait a little bit to see if the transmitter comes back or if the signal comes back, and not have to go through the whole dance of changing gains all over again. There is an interesting shortcut that we noticed when in the idle state, the AGC is at the very high gain setting. But if you have a transmitter right next to the device, you can very quickly end up needing to go from high gain to low gain. And the idea is that as you're changing gains, you might not want to wait for the whole group delay to expire between the transition from high to mid, because as I'll show in one of the future slides, basically it's a ramp. So if the ramp doesn't have enough of a downward trend, you can very quickly shortcut the transition from the high gain setting to the mid gain setting and realize that you need to go to the low gain setting. So this kind of improves the settling time of the AGC. So this AGC wound up getting tested on the with a E4438C VSG. It's kind of an old device, but it's amazing for outputting small tones or small bandwidth tones. It has a bunch of programmable settings for adjusting everything from the amplitude to the frequency and the stops that the VSG takes in sweeping from the start to end of your program settings. So using baudline and enabling the AGC, this shows the transition from I believe, what was it? From a minus 100 dBm signal, which is on the left, and the transition to a minus 25 dBm signal. So in the top image is basically the lack of any AGC. So you go from a nice sine wave over to a clipped sine wave. The lull in the middle is an artifact of the VSG, because the VSG has some internal relays that it needs to flip in order to get the appropriate gain setting out. So that flat line in the middle has nothing to do with the receiver and has everything to do with the VSG. So once the AGC kicks in, you can kind of see that in the bottom image that the 100 or the minus 25 dBm signal starts looking more like the minus 100 dBm signal. The reason why there's a frequency shift in between the minus 100 dBm signal and the minus 25 dBm signal is because of the settings set in the E4438C. So the E4438C sweeps, so it was basically toggling between minus 100 dBm and minus 25 dBm while also changing the frequency just to help kind of encode, to visually encode to me what is happening. And yeah, as you can kind of see, there's an initial spike in the AGC-enabled graph, but the AGC very quickly comes in and adjusts the gains of the receiver. And after sort of like what appears to be about a third, like pi over 3, it actually is fully settled, and it starts looking like a nice sine wave. And then let me see if I can just get a quick video up. Whoops, that is not what I meant to do. Yeah. So here's a GQRX capture, a side-by-side GQRX capture of the bladeRF running without an AGC and the bladeRF running with an AGC. And this was a signal that was split and sent down to 2 bladeRFs. And here's a side-by-side capture of what is happening. There was no software modification to GQRX. This was basically 2 instances of GQRX, and then things were just edited together in post-production. So here is, oh, give me just 1 second. The audio on this video is a little bit distracting. All right, here we go. So basically what is happening here is the E4438C is sweeping from minus 120 dBm up to minus 20 dBm in 3 dB increments. And the thing on the left will show the bladeRF without an AGC, and then the image on the right will show the bladeRF with the AGC enabled. And as you can see, the the signal is kind of deviating from the pedestal, and very soon it'll switch over to the medium gain setting, and the capture without the HEC will start getting more and more distorted as the spectral skirt phenomenon exhibits itself. Meanwhile, the HEC enabled bladeRF is able to maintain a really decent signal-to-noise ratio. So this is just a visual of the HEC running, and yeah. Oops. Then there was another GQRX test that I wanted to run, which was to change, as I said, both the frequency and the gain. So before the AGC is enabled in the bottom half, you see a lot of harmonics, you see a lot of distortion, and as soon when the VSG is outputting a -25 dBm signal, but as soon as the AGC is enabled, you no longer see any kind of distortion. So the AGC enabled in this waterfall is above the AGC enabled line. I probably should have put an upwards arrow instead of a left arrow. So there's a bit of FPGA development to this to get it to work, as I said. So the interfaces that have to be implemented for the AGC core are some way of getting the IQ samples. So in this case, it's from the LMS 602. And also a way of being able to communicate with the front-end transceiver to adjust the gain settings. So there's one issue, which is the SPI bus, which is the way of changing the gain settings, was also used by other things in the bladeRF FPGA image. So basically there was a SPI bus arbiter that had to be implemented to allow the command line and the AGC to be able to use the SPI bus without affecting one another's operation. So the AGC was a round-robin, priority-driven round-robin arbiter, and the AGC was given the absolute greatest setting, or priority, I'm sorry. And this is just a simulation of the arbiter. You can't really read it, but basically what it's showing is a bunch of permutations with the AGC and the command line NIOS both trying to get control over the SPI bus, and there being arbitration being done by the HDL arbiter. So in addition to just changing gains, there's a couple of issues with these 0IF transceivers. The two most common ones are DC offset and IQ imbalance. So these are analog phenomenon, and the best way that we can do is to try to combat them by adjusting compensators in transceivers, or try to do so digitally. With the LMS6, there are analog compensators that can help bring the DC value down and also improve IQ balance of the transceiver. However, when you're changing gain settings, in order to not slow down the AGC even more, changing the DC offset may not be the most, it may not be the best thing to do. Another issue is the DC offset. When you calculate the power of the incoming signal, you basically square I and you add it to the square of Q. So if you have a DC offset, that DC offset might trick the AGC into believing that there's another hot signal coming in, so that it should go from a high gain setting to the mid gain setting to the lowest gain setting, despite the fact that there may not be something that requires it to go to the low gain setting because of this like phantom DC offset that pops up. So what had to be implemented was a DC offset correction for the AGC. So ignore the IQ imbalance stuff for the purposes of the AGC because there was no IQ imbalance correction done within the AGC. However, the DC offset correction was kind of implemented in a pretty interesting way, I think. So for the 3 gain settings that exist, all the IQ imbalance compensators and DC offset compensators have to have completely different values because your DC offset and IQ imbalance are basically gain setting dependent and temperature dependent. So in order to figure out what the DC offset would be at the 3 different gain settings, we wrote a routine that basically would go in and create a lookup table for the DC offset at each one of those 3 gain settings. So then the idea is that as the AGC is running, it's telling the this DC correction lookup block what value to subtract from the incoming signal. So then the idea is that instead of removing the DC offset in analog, we're removing it in digital, so or within the FPGA. So then this is basically a dance that is done between the software bladeRF and also the HDL inside of the FPGA. So the software runs a bunch of calibration routines, figures out what the DC offset is at each one of the 3 gain settings, programs it into the DC offset lookup table, and then as the AGC is running, it knows what gain it's going over to, and then basically selecting the appropriate DC offset to subtract from the incoming signal. So yeah, this is just a signal tap capture of the AGC running, and yeah, and just wanted to take a couple of moments to kind of make everyone aware of the bladeRF 2 micro. It's a revamped version of the bladeRF. It's a Cyclone 5 FPGA 89361 based SDR. It's basically 2x2 MIMO, 61.44 sampling rate RF front end with a 56 megahertz IBW. It's the standard 89361 transceiver with 2 variants for the FPGA, so a 49 kill element FPGA and a 301 kill element FPGA variant. And one of the things that we like the most about it is the little bias T modules that we've come up with, which are impedance matched to the device. So we have amplifiers, LNAs, and soon enough we'll have a few filter boards. So yeah, let me see. Oh, 4 minutes over. Any questions? Oh, I feel like I started 4 minutes late, and it's 4 past noon, and I think everyone wants lunch. So, okay.
So oh yeah, there we are. So no, we have plenty of time for questions, and yeah, lunch is still in the process of being set up. So if we can have a little conversation here, that'd be the perfect segue into hide the fact that we're not actually ready yet. Where's the other mic? Does someone have that? Derek. So I think Robin raised his hand, and there's a bunch of other people around there.
I've got one right here.
Actually, you go ahead, go first, then I'll walk to these guys.
Cool, thanks. Great talk. I was just wondering about the dynamic range of the ADC. Any reason you didn't use the effective number of bits? Because I see it's 12 bits.
Yeah.
So the effective number would be lower, right?
Oh yeah, it would definitely be lower, but that's like the theoretical absolute maximum that it could be just based off of the number of bits that exist in the transceiver or in the ADC.
And if you use the effective number in the calculation, we'll get a lower dynamic range.
Yeah.
So how would it translate down the line?
So, right, if your ENOB is way lower than that number, and the idea is then you would have to add additional gain stages to be able to have this like continuous range between your high gain setting and your low gain setting, because you're right, like the effective number of bits is the thing that you should be using more than just the ADC bit values. So if the ENOB is very low, then you need a lot more granularity in your gain settings, or in your gain stages. So then you'd have to introduce more gain stages to be able to go from like a high gain setting to a low gain setting without having issues where you are not receiving signal correctly.
Yeah, thanks. That was a great talk. Yeah, so I was just wondering, in terms of the AGC, when it's implemented in the FPGA, do you see issues with like super fast bursty signals like ADSB where you need to catch this and decode the first bit? Because the latency of things, you're not, unless you're a super oversampling, it's going to be harder.
Right, exactly. So the AGC sort of runs on the sample clock, and there are certain design decisions that we have made when we've had to deal with waveforms where you're basically starting to receive data without sort of any kind of real preamble. But ADSB does have a preamble to some extent. If I remember correctly, it's just a bunch of ones and zeros before the actual payload starts. So you could use the beginning part of the ADSB.
Well, it has a barker that you're supposed to decode, yeah.
Yeah. But in case there's just data coming straight on the line, you may want to use a faster settling time IIR so that you can more quickly jump onto it and then rely more on hysteresis to not have the gains change under
Well, so how does that compare to the bladeRF2 where the AGC is actually in the transceiver?
Right. So with the bladeRF2 being an 89361 device, there's a slow AGC, a fast AGC, a hybrid AGC, and a manual AGC setting. So with some of the waveforms that we've developed, we've kind of wanted to have, like your guys' AGC is great, but in order to kind of like speed up our own development, the idea is to have an AGC that we can kind of depend on exhibiting the same sort of settling times and behavior between different devices. So while we do use the internal ASICs AGC, for some waveforms we do kind of rely on our own AGC. Yep.
Oh, thanks, good talk. Can you give an indication of what is the settling time?
Of what is what?
What is the settling time? I'm just kind of curious of what roughly is your settling time.
It was, let me see. It was several hundred nanoseconds, so about 700, I guess that's more than several, but it was about 1 microsecond. So about 0.7 microseconds, about 1 microsecond.
So Phil Karn is next. Who else has a question? Just so I can schedule. Actually, Derek, can you go over there? Okay.
Oh, okay. 2 questions. You said that you reduce gain when the sample goes within 3 dB of full scale.
Yep.
Is that an absolute peak, or is that an average power? And if it's, how long is it averaged over?
So it depends. For some logic within some of the waveforms, we decided to very quickly switch over as soon as we saw something within 3 dB of full scale.
An instantaneous sample.
Instantaneous.
Okay.
So between the IIR having an upward trend and a single sample that was within 3 dB of full scale, you could kind of make a reasonable decision as to jumping from the highest gain setting to maybe the low gain setting without even stopping over in the middle gain setting.
The second question, do you pass the gain settings to whatever's consuming your output?
There is a PR in the work for adding the gain setting, or the current gain setting, into the metadata field.
Okay, I've been working on this exact problem, which is why I'm interested. I mean, I see 2 ways. You could set it as explicit metadata, or you could fold it into a floating point value, so you get an absolute value that's independent of the gain setting.
Actually, yeah, that'd be pretty interesting, turning
Yeah,
the
there is a
samples.
16-bit half-precision float now.
Yeah,
That's interesting.
yeah, okay.
Thank you.
So we had another question over there, and then.
I just had a question. You said it was tied to the signal, the AGC is being tied to the signal of interest or whatever. So is this a channelized AGC versus the full wideband?
It is not
of
a
the-
channelized AGC. It is a wideband AGC.
Okay, so it would work on an interferer, not the signal of interest that you're processing?
Right. It would not. This is more for datacom purposes, more so than operating in an adversarial environment. So if someone does put in even just like a CW, it would pretty much jam the AGC.
Okay, so it's pre-channelization or anything like that? It's just over the full bandwidth of the ADC?
What is what?
It's the AGC is operating over the full bandwidth of the ADC?
Right.
Okay.
That is correct.
Okay.
So we have another question here, EJ.
Hey, so just to ask about a specific application, have you tested this in any like common waveforms like that are bursty and have near far problems? Like someone would want to capture like a Wi-Fi, like a 802.11, channel, and how does that work?
Yeah, this was pretty much designed with 802.11 in mind.
Oh, great,
So,
cool.
Yeah.
Actually, does someone know about the status of lunch in this room? You could give me an update, because I
I'll
think
check.
everyone's interested.
I'll check.
Okay, while Derek checks, I'm sure I think I saw at least one more hand somewhere, but I've forgotten where it was. No? No more questions? Okay, well, there's no more questions, and we'll have a little bit of a downtime before we actually eat. So first of all, Nuant is actually a sponsor of the conference, and for that, and also for this talk, I think I'd like a big round of applause.
Thank you.